Hello, welcome to the second session of Business Maths, where we'll be looking at the continuation of differentiation, chain rule, and differentiation application to elasticity under economics. The session objectives is that we should be able to get or understand the concept of the chain rule, the generalized power function, differentiation of special functions, and partial differentials, i.e. natural logarithm and exponential functions, and then how to deal with applications of differentiation to elasticity. On our next slide, we have what is called the chain rule or the U-substitution approach. It's an old rule that is used to deal with functions that you can't easily differentiate. Those functions are called composite functions. Suppose y is indirectly related to x and u directly related to both x and y. Then one can find dy over dx by applying the chain rule, which is saying that the differential dy over dx is equal to dy over du multiplied by du over dx. It is u substitution here because one of the functions to be given to you, right? One of the functions in the term given to you, right, will be represented with u. That is why it is called u substitution. So the name chain comes from the fact that the formula could be extended to any length as long as a feasible relationship exists. So for example, dy over dx as a differential is equal to dy over du multiplying du over dm multiplies dm over dk by dk over dp, and then by dp over dx. It's simply telling you that this chain rule here is a fundamental concept under calculus that is used when you have consumption of what? Functions. That is, you have one function in another function, or you have one function inside another function, right? So let's look at a practical example under chain rule and how we go about it using this formula over here. So an example says that differentiate the function y is equal to x cubed minus 1 all to the power 7 with respect to x. Differentiating y with respect to x. So as I said earlier, one of the functions will be represented with u. So which of these functions? It is the one in the bracket, x cubed minus 1, which is the inner function. 7 here is an outer function. So this is the composite function I was saying. So let x cubed minus 1 be equal to u. So you find the differential of u with respect to x. That is du over dx, which will give us 3x squared. And we'll rewrite the question or the function again. So it is y is equal to, now we said that x cubed minus 1 is what? U, right? So it is y is equal to u to the power 7, right? U to the power 7, and then we can differentiate y with respect to u because this x cubed minus 1 is now u to the power 7. So dy over du here will give you 7u to the power 6. Right. The next step is to back substitute this u, put the actual term of u here because the function was given in terms of x, not in terms of u. So we'll say that this dy over du is equal to 7 into bracket x cubed minus 1 all to the power 6. Right. So we'll just put these two functions here back into the chain rule formula, which says that dy over dx is equal to dy over du, which is 7 into bracket x cubed minus 1 all to the power 6 by 3x squared, which is our du over dx. This is how we deal with composite functions using the chain rule. Let's look at a practical example where I'm going to apply what we've learned here in economics or in the business perspective. Here's a practical example. Marginal revenue product. The rate of change with respect to the number of employees. Right? So a manufacturer determines that m employees will produce a total of kill units per day, where kill, which is quantity, is equal to 10m squared plus 10 all squared. Let R be revenue. Right? So if demand equation for the product is P is equal to what? 1000 minus 5 kill. Determine the R over the M. That is the rate of change of revenue with respect to a change in the number of employees, also termed as marginal revenue. So basically, this question here is asking us to find our marginal revenue, which is the R over the M. Remember, to find the marginal revenue, it is the differential of the total revenue function that you have. Right, is the differential of the total revenue function. So we have to find our total revenue. Okay, where we've been given what price here, which is total revenue is equal to what price times quantity. So let's look at the solution of how we go about it. So look for our total revenue, which is equal to price times quantity. So we say total revenue is equal to the price, which was given as P equals 1000 minus 5Q times Q, which is what you have here. If you multiply through by the Q, you get 1000Q minus 5Q squared as your total revenue. Right. So using the chain rule formula, we can say that our marginal revenue, the R over the M, is the change in your revenue over your change in the quantity times the change in your quantity over the change in the number of employees. So the R over the Q multiplying the Q over the M. Right. So we have to look for the R over the Q here first, and we'll look for the Q over the M. So the R over the Q simply means that differentiate your total revenue function here with respect to quantity. So the R over the Q will give us what? 1000 minus 10Q, i.e. the differential of 1000Q minus 5Q squared. But we're given in the question that quantity, we had a quantity function to be 10m squared plus 1 all squared. So we just substitute it here in the function. Okay, so we say 1000 minus 10 into bracket 10m squared plus 1 all squared. Right, so we are done with the dr over the q. The next thing is to find our dq over the m. So the q over the m is also about the quantity with respect to the number of employees. Right, so differentiate this quantity function here with respect to what? M, which is the number of employees. So to differentiate that, bring the power in front of the function, and then you have 10m squared plus 1 all to the power 2 minus 1 here, you get 1. Then you multiply it by the differential of what is in the bracket, right? So 10m squared plus 1, right, times 20. Okay, so 2 here times 20 will give us what? 40 into brackets 10m squared plus 1 here, right, always to the power 1 is the same as this function over here, right? So we would say that we'll just substitute this function over here, right, and this function here into the chain rule formula we have over here. So the R over the M, which is our marginal revenue, is equal to 1000 minus 10 into bracket 10m squared plus 1 all squared multiplying the Q over the M, which is 40m into bracket 10m squared plus 1. Right. So what do? The next thing is that we are going to expand this bracket we have over here. Okay. So we'll say that 1000 will multiply 40m into bracket 10m squared plus 1, and that will give us 40,000m into bracket 10m squared plus 1. Right. And then this minus 10 into bracket 10m squared plus 1 all squared will also multiply 40m by what? 10m squared plus 1. So this function here, right, by this gives us what? 400m into bracket 10m squared plus 1 all to the third. Remember, this is having a power of 2. This function has a power of 1. So 2 plus 1 gives us 3 indices, right? So this is how we go about the chain rule in the application level or in the business sense, right? This is our marginal revenue function now, and you are done with the question. Okay, so let's move on. We'll be looking at the next one, another rule under differentiation, which is called the generalized power function. Right, generalized power function. We can also use the power rule to do that because it is raised to a power. Right, that's the idea. So given that, or given the function y is equal to x to the power n plus 1 all raised to the power p, the derivative with respect to x can be obtained using the general formula. Right, so bring the power in front of the function x into bracket, bring the power in front of the function x to the power n plus 1, reduce the power of p by 1, multiply by the differential of what is in the bracket, x to the power n plus 1, right? Bring the power in front of the function, reduce the power of p by 1, multiply it by the differential of what is in the bracket here, xn plus x to the power n plus 1. So this formula here, or this function here, can be also rewritten, or it can be written in this way, right? So where you have a function u to the power a, it is raised to a power. So you can use a generalized power function, which is saying that bring the power of a in front of the function. So that gives you au. Reduce the power of a by 1, that is a minus 1. Then you multiply it by the differential of the function, which is your u here. So du over dx, right? Note that this generalized approach is in fact the chain rule, where dy over du is equal to au to the power a minus 1 times, right, a minus 1 times your du over dx, right? Please take note of that, times your du over dx. All right, moving on to the next slide, where we'll be talking about the basic rules of logarithm. So a common logarithm is a logarithm with a base of what? 10. So a common logarithm is a logarithm that has a base of 10, which could be written as log x or log x base 10. It is defined as the power to which 10 must be raised to equal to x. So these are some of the rules governing the common logarithms, right? We have the first one, which is called the product rule. So product rule, you can see that it is log of a multiplying b, right? So log into bracket a times b. So where you are multiplying, right? So those of the terms, or the terms that are multiplying in a bracket here, becomes what? Addition outside, right? So we have log a times b. It is equal to log a plus log b. The quotient rule is when you have log a divided by b, right? So the terms that are dividing here, a over b, becomes minus, or yes, it becomes minus outside. So we have log a over b, it is equal to log a minus log b, right? So we have the next one, which is the power rule, where you have log a to the power n. Log a to the power n here. The exponent inside the bracket, which is n here, right, becomes what? Multiplication outside. So you can see that log a to the power n here, then n here is rather multiplying log a. So the exponent becomes multiplied by what we have here. Okay, so the exponent becomes multiplied. The exponent here is multiplied by what we have, log a here. Okay. Looking at the next one, where we have what is called the identity rule. Identity rule is just saying that if you multiply log 1, right, if you have log of 1 is equal to 0, right? And then the 0 rule is also saying that if you have log 10 to the base 10, it is equal to 1. Chain of base, right? Chain of base is a rule that lets you convert logs or logarithm from one base to another using a common logarithm. So here you can see that we have log BA. It is equal to log A over log B, right? So it's just helping you to convert logarithms from one base to another. Okay. On the right hand side here, we have the natural logarithm, or what is called ln. The rules of natural logarithms, ln, are derived from the properties of the exponential function with base e. And they are essentially the same rules as for other logarithms, but with the base e. Okay, so natural logarithm is a logarithm with the base e, right? Where the base E over here is approximately 2.71828, right? That is the base E here. So it is written ln of x instead of log E or log x base E. Okay, it is written as log or ln of x instead of log x base E. That's what they are trying to say. Okay, or that is what this natural log simply means. So we have the product rule as well, where we have natural log of n, natural log of AB, sorry. So ln of AB is what? Ln of A plus ln of B. Quotient, the same thing. Ln A over B will be ln A minus ln B. Same applies to the power rule. You have the natural log of 1 is 0. The natural log of the base E, or natural log of E is 1. The natural log of 1 over x is minus natural log of x. Right. So let's move on to the other aspects of the topic, or the other areas of the topic. We'll be looking at examples under what we call special functions. So what are special functions? Special functions are also rules under, or they are also functions that we deal with under differentiation. So you could have something like y equals ln of x. The general form of the derivative of this function is just saying that dy over dx, dy over dx, which is the differential, is equal to 1 over the function times the differential du over dx is the differential of that same function you have here. So what is the function? The function is such that if this ln is being taken away from the term, what is left here is x. X is the function we are talking about, right? So dy over dx of something like this ln of x is such that it is 1 over x, which is the function, times the differential of x, which is 1. So this is an example to explain what you are saying. Find y prime if y is equal to ln of x. So we would say that which of these terms here, or which one is our u, or which one is our function? It is the x here when the ln is taken away, so x. So let u be equal to x. Then we'll say that du over dx is equal to 1. The differential of x is 1. So back into the formula, it says dy over dx is equal to 1 over the function times the differential of that same function. The function here is x. So 1 over x times the differential of x is 1. And that will give us 1 over x, which is simply telling us that the differential of the natural log of x is 1 over x. Let's look at a more complex example where we would have to deal with the same special functions, but a bit tougher than what we just did. Right? Find y prime if y is equal to ln of x squared plus 5 all squared. First of all, you have to identify what our function is. Our function is x squared plus 5 all squared. Let u be equal to that function. And find the differential of that function. So du over dx here will give us, bring the power in front of the function. So 2 here in front of the function, multiply it by x squared plus 5, reduce the power by 1, that is 1 over here. Then you multiply it by 2x. Okay, and that will give you the du over dx. So the next thing is I just substitute it back into the formula with Ledge length, or we just talked about. So dy over dx is equal to 1 over the function, which is x squared plus 5 all squared, multiplied by 2 into brackets x squared plus 5 times the differential of what is in the bracket, which is what? 2x. The next thing is that we multiply this 2 here by 2x. That will give us 4x. 4x by 1 gives us the same 4x. So you would have 4x into bracket x squared plus 5 all over x squared plus 5 all squared. But the x squared plus 5 that you have here will cancel one of these x squared plus 5 that you have here, which is raised to the power 2. And you'll be left with this final answer, right? So the differential of this function here is equal to 4x over x squared plus 5. Right. Another approach for this problem is to know that according to laws of logarithm, y is equal to ln into bracket x squared plus 5 all squared. Then you have 2 ln into bracket x squared plus 5. Then if x squared plus 5, if u is equal to x squared plus 5, then dy over dx is 4x over x squared plus 5. This is the same procedure. It's just explaining how you can go about this in a different idea or a different approach, right? So we can use these basic steps to solve any natural log functions, right? Let's take a look at another example. Find y prime if y is equal to natural log of x squared plus 2 all raised to the power minus 1. We have to identify our function. The function here is what? It's x squared plus 5 all squared minus 1. That is, let u be equal to that function. Then find the differential of this function, du over dx, which is what? Minus 1 right. For this question here, so we would say that u is equal to the function in the bracket, which is the function here, which is x squared plus 2 all raised to the power minus 1. Then the differential of this u with respect to x, that is du over dx, is equal to minus 1 multiplying x squared plus 2 all raised to the power 2. Bring the power in front of the function, reduce the power by 1, gives you minus 1, that is minus 2. Multiply it by the differential of what is in the bracket here, x squared plus 2, that will give you 2x. So back substitute it into the formula, or just bring it back, substitution. So we have dy over du being equal to 1 over the function here multiplied by du over dx, which is this function. Then negative 1 times 2x gives you negative 2x. And if you reduce this, x squared plus 2 all to the power minus 2 over x squared plus 2 raised to the power minus 1. We're going to be left with x squared plus 2, right, indices. Or simply, you can go by the logarithm approach and you get the same answer for this function. Right, so let's look at the next one, which has to do with exponential functions. Okay, so you have exponential functions here. Given a function such as y is equal to e to the power x, the general form of the derivative is dy over dx being equal to e to the power u by du over dx, right? So the caveat here is that if you differentiate e to the power x, you are going to get e to the power x. So first of all, write the function as it is. Don't do anything to that function. Then you multiply it by the differential of that function. How do you get a function I'm talking about? Or what are you going to represent as your u? If you cover this e, what is left on top of it is the x, that is the function. Or what is on top of the x here, the e here, which is x, is your u. So let u be equal to x, right? The differential of x is du over dx. That will give you 1, right? So write the function as it is, i.e. e to the power x multiplied by the differential of x. That will give you 1. E to the power x by 1 gives you e to the power x. That's why I was saying that the differential of this e to the power x gives you the same thing, right? Given a function such as 2x to the base 2, the general form of derivative is the log u to the base b dx is equal to 1 over ln of b multiplying u times du over dx. Let's look at this explanation here as to this logarithm approach. So log x to the base 2 is equal to y, means that this base of 2 raised to the power y should give you x. So 2 to the base, or 2 to the power 2 to the power y should be equal to x. An example is that when you have log 8 to the base 2 is equal to 3. Simply is because, or it simply means that this base of 2 raised to the power 3 here, or raised to the power what number, should give you 8. Remember, 2 raised to the power 3 is equal to 8. Same here, log 1 base 2. Is that what number raised to this power, what number are you going to put it on top of this 2? Or 2 raised to the power what number is going to give you 1? Remember, 2 raised to the power 0 is equal to 1, right? Because any number raised to the power 0 is 1. Same applies to this last one over here. Now, this is how you deal with the logarithms. All right, let's look at an example under the exponential function. This is what I just explained. U is what is on top of the e, so u is equal to x. Du over dx, the differential of x here is 1. So to find the dy over dx simply means that keep the function as it is, because if you differentiate, you get the same thing. Then you multiply it by the differential of what is on top, i.e. x, which is equal to what? 1. E to the power x times 1 gives you e to the power x. Find y prime if y is equal to this, e to the power x squared plus 1 all squared. Keep the function as it is, right? dy over dx, keep the function as it is, right? Multiplied by a differential of what is on top of the e, which is x squared plus 1 all squared, becomes the function, or becomes our u. So bring the power in front of the function, reduce the power of 2 by 1, then you multiply it by the differential of what's in the bracket. Differential of x squared plus 1 gives you 2x. So keep the function here again. You multiply 2 by 2x. That will give you 4x into bracket x squared plus 1. Right. So this is how you go about the exponential functions. Let's look at where we have to apply what we've learned here in the business sense, or under what is called economics, right? So where we have elasticity of demand, or elasticity, we'll say that is a degree of responsiveness, right, to a change in the quantity of a commodity with respect to the change in the price of that commodity, right? So we'll say it is change in quantity over the change in price, where Q is the quantity and P is equal to the price. So the change in Q, which is our quantity, is equal to dq over Q. Change in P, which is our price, is dP over P. So what is the elasticity? It is dq over dP multiplying, right? Multiplying dP over Q. That is the elasticity. So dq over dP. The formula is dq over dP multiplying P over Q. When Q is expressed as a function of P, then the elasticity becomes function of price. That is the meaning of this formula over here, right? So that's the same thing you are having here as the elasticity formula. So let's look at a practical example where we are going to use this formula over here, right? So it says that the demand function for a product Q, which is quantity, is equal to P squared minus 40P plus 400, right? Where Q is greater than 0. This simply means that as a producer, say you are a manufacturer of a certain product, right? Right. So say you are a manufacturer of a certain product, you can't say that you produce negative quantity of your products, right? Always the quantity produced is greater than what? 0. That's the interpretation of this thing over here. So find the point elasticity of demand right here. So to find that, we say that it is dq over dP, change in quantity over change in price, times price over quantity. So we have to find our dP over dq, which is what? P squared minus 40P plus 400. So dq over dP will give us what? 2P minus 40 times P. We don't know P, so P here over Q. Q has been given as this whole function you have here, right? So over P squared minus 40P plus 400. 2P minus 40P multiplies P. That gives you 2P squared minus 40P all over P squared minus 40P plus 400, right? So a further question could be that find the point elasticity when N is equal to P is equal to what? 15. So just substitution. Wherever you see P here, you put 15. And that gives you 2 into bracket 15 squared minus 14 into bracket 15 over 15 squared minus 14 into bracket 15 plus 400. And we have our point elasticity to be negative 6. The interpretation is that a 1% change, right? So a 1% change or a 1% increase in the price of their commodity or of their product leads to a 6% decrease in the quantity demanded of that same product. Right? So if the price increases by 1%, the quantity demanded decreases by 6%. It also means that there is a negative relationship between price and quantity of that product or commodity. Thank you for this time. We'll be looking at the other sections another time. Goodbye.